serverless cloud architecture patterns, or as it is said in the description, cloud architecture patterns and how to implement them in a serverless way. I shortened the title a bit, just like we did with my current company. We had a company name that was so long that when you actually enter it into web forms on any web app on the internet, it actually complained because no one has a company name that is that long. I started working with cloud early 2015. And I started working on a system that was going to collect information from end users, coming from their mobile phones. That was my first system that I built, the first system I designed. And we figured out that, some investigation, what we want to do is go serverless. So we implemented a good way where we collected information over a REST API, implemented in AWS API Gateway. We stored the information onto SQS for later processing. Little did we actually know that the pattern that we used had a name. And that has been the common case I've seen over the years, that we're using patterns and we don't really realize that these are a common thing. So that is what we're going to talk about here today. I'm going to share light on some of the cloud architecture patterns that I use the most, the things that I think is the most important. So it's a highly opinionated talk from that point of view. This is my view. So today's agenda, we're going to do some introduction, because I'm going to need to introduce some terms and terminology that you need to understand, that we need to have a common ground. We're going to move over, talk a bit about resiliency, event-driven architectures and messaging patterns, queuing, and let's round everything up with a short summary. But who am I? My name is Jimmy. I'm the father of 2 girls, which basically makes me afraid of nothing. I'm a serverless and event-driven architecture fan. I've been working with serverless, as I said, since 2015. When I started working with AWS Lambda, there was no environment variables, and the max RAM was 1 gig. That is how Lambda old I am. I'm an AWS ambassador, AWS community builder as well, and I run and host a lot of AWS meetups here in the region. On my daytime job, and yes, I do have a daytime job, even if people sometimes keep asking me if I do, I work as head of AWS at Sigma Technology Cloud. We are a cloud-specific company in the Sigma Technology Group, located here in Malmö and in Stockholm. So let's start with a short introduction. We need to talk about producers, consumers, and routers, because we're going to talk about event-driven architectures in this talk. What is an event producer? Event producer is a system or component that produces events, and puts them onto a router. Producers can be AWS services natively. It can be client calls over REST APIs. It can be SaaS services that we integrate with, and many, many other things. Event routers are the systems or the components that route these messages. It can be event buses used in Amazon Event Bridge. It can be queues like SQS. It can be SNS topics in AWS. And it can even be IoT Core. The consumers are the components and systems that read and consumes these events. AWS services, API endpoints, SaaS services, or other things. Talking about orchestration and choreography, what is the difference? Orchestration is a control pattern where we have a single orchestrator that controls the flow in our system. Typically, it's an Amazon step function that coordinates the different functions and different flows that we have in our step function. In choreography, it's a decentralized system. We have a decentralized way to distribute the events. We have the system actually dance to these events and perform tasks without knowing about each other. There's no central control organism. We need to talk about the envelope wrapper, because we're going to use the envelope wrapper a lot in this talk. What is an envelope wrapper? The envelope wrapper is a way for us, just as you send a letter to someone, you take the letter and you put it in an envelope. You do the same here. You take your original messages and you put it into an envelope. And we do that so we can separate the information. That way we can introduce advanced filtering, and we can add information about the message itself onto that envelope. A good practice is to make sure we use predefined keys, because then both the producers and the consumers in the system knows about the envelope keys and can read and add them. A drawback is, of course, that we add additional overhead to our messages since we add information to our envelope. A classic pattern when it comes to metadata to envelope wrappers is a metadata data pattern. This was first mentioned, I think, back in 2020 by Sheen Brisals of the Lego group. He's a heavy user of event-driven architectures, and Lego is as well. So he introduced and talked about this metadata data pattern. What is the metadata data envelope? The metadata contains information about the message. It can be an event ID for tracing. It can be a retry count, and I will come to that one later. In the data part, we have the payload, the information itself. So in this case, it could be the path to an S3 bucket. It can be a key in an S3 bucket for an object that's been created. So that is the message, the payload. And in the metadata, we add additional information about the message. What is commands and what is events? The similarities between a command and event in an event-driven architecture is that both are messages, and both are in JSON format. And when I say it's going to be in JSON format, I mean use JSON. Don't use XML, don't use plain text, don't use protobuf. Use JSON. It's a good foundation for an event-driven system. Easy to parse by machines, and it's easy to read by humans. A command is something that is proactive. It has an intention, it has a targeted audience, and it can be both asynchronous and synchronous. A good example of a targeted command is create user. It has a target for the user service to create a new additional user, and it's proactive, it has an intention. An event is reactive. It's often a broadcast, it doesn't have a target. It's informational. Example is user created. So user service broadcasts into the system saying that, hey, a new user has been created and added. So some common grounds. Now we can move over. Let's talk about some resiliency patterns and good resiliency patterns in cloud. The first one is actually one I brought up in the beginning. Storage first. It's a way to put data in the center of the communication. It's a good way for us to introduce a good durable and availability in our system by storing the messages first. So what we do is we take the message, we store it, and then we process it. And it creates a very scalable system design. So the benefit is that we have assured data durability, that we make sure we store the message before we're processing. Because if we do it the other round, we have synchronous invocations of the processing logic. If the processing logic fails, we would lose that message. It's a good way for us to level the processing load. So if we store it in a queue, we can then process the queue in our own pace. It's very good for high volume data ingestions. Say that you have a producer that is really fast, produces events in a rapid pace. The consumers, on the other hand, is not that fast. They're not that high speed. If we would have a synchronous invocation of the processing logic, the slowness of the consumers would impact the speed of the producers, but the producers need to wait. By introducing the storage first pattern, we take the message, we store it, and the producer can move on. It's also a good way for us to deduplicate data. So if we get several messages with the same information, we can deduplicate them in the queue before we even process them. What we need to consider in the storage first is, of course, potential increase for latency. We store the message, then we process, so we might have an increased latency in that case. The architectural complexity grows as we add more components. But most important, there is a need to a very robust storage solution. If you have a storage solution for messages that is so-so, that would impact the durability and availability of the system. Using like a service like SQS is perfect for this. It's very resilient and very durable. So, an example, and I'm going to use, throughout the talk, I'm going to use examples from a pizza shop, so to say. Let's say that we have our order service. The customers adds orders into our order service. What we don't want to do is we don't want to lose orders coming from the customer, of course. We don't want to lose a customer's pizza. So what we do is we add them into an SQS queue directly here. And then we can have our other parts of the pizza service process the orders and start the transactions. A different way would be to have an IoT application. It could be like say the oven of a pizza place that continuously sends information about status of pizzas, time, and how long they have been in the oven, and so on. We don't want to lose that information either. So we introduce Kinesis here to catch the messages directly, store it, and then process it. And after our event bridge, we can add an SQS queue and then process those pizza messages coming from the oven in the Lambda function. This way we will not lose messages, we don't lose orders, and we don't lose information coming from ovens or something like IoT connected devices. The next pattern is a circuit breaker pattern. What is a circuit breaker? A circuit breaker is a way for us to wrap a crucial part of our system inside a breaker, like a light switch, on, off. What that does is it prevents system overload, and it helps us maintain system resiliency. It helps us avoid cascading failures in the systems. So if one service fails, we don't want to impact everything else. It helps us protect system resources that are crucial to our system. And it provides us with failover possibility and actually improved user experience. If you take a look, some things to consider, of course, is the need for configuration. And there is always a risk for early circuit breaking. So should we break the circuit just because we have one failure? Or do we need to wait for like 10, 15 failures before we break the circuit? There's an absolute requirement to have a good observability so we understand the health of our components in the system. System complexity grows since we wrap things. And we need to decide when and how to recover from a failure. So if we're going to look at a way to implement this, a circuit breaker, we can use the AWS step function. Let's say that we have a processing Lambda. In this case, we have, once again, our pizza place. So we have orders in a queue. Now we want to process those orders, and we start to bake the pizza. But if the oven is broken, we don't want to keep sending requests to that service that handles the pizza baking, right? Because there's no point in sending those requests, because the oven is broken. So what we want to do, first of all, we check the status of our circuits. If it's closed, then everything is good. We process our things. We call the bake service, add the order to the oven. If the circuit is open, meaning that nothing can flow, we need to wait. We need to take a step back. We keep storing the messages in the queue. Combine this with storage first, and you have a very resilient pattern. But we don't want to wait forever. So if the circuit is open, we can have a timeout saying, okay, if the circuit is open, I will still retry every 15 minutes just to see if something has been fixed. So we would check that time. And if we have in the process saying, okay, 15 minutes has passed, let's retry, we do that. If we still fails, fine, we do nothing. If it succeeds, we might close the circuit again. And the final part, of course, in the processing, in a step function, is to open or close the circuit for us. So if you look at that in a more step function way, in the flows, this is basically what we do. We have our circuit status in DynamoDB. We check that status. Is it open or close? We use a choice state to determine if it's open. We check the timestamp. Should we retry? If we should retry, we do a retry invocation on our processing lambda. The processing lambda would then retry or then open and close the circuit. If the circuit was closed from the beginning, we just do it in a processing way. This is a very highly efficient way to wrap a lambda function inside a step function to add a circuit breaker. But what if we can't use step functions? Let's say that we have our order service, takes a service over an API gateway, puts that into SQS queue, and then we want to process those orders for the pizza place. We can't have SQS invoke our step functions directly. That's no integration point today in AWS. So we would use a Lambda function in that place. So how do we do that? We can't wrap the Lambda function. How would we do that? Well, what we can do is that our processing Lambda sends information, sends logs, metrics to CloudWatch. If we start getting failures from that Lambda function, CloudWatch would trigger an alarm. That alarm can then disable the Lambda integration on the SQS queue. So we remove the Lambda integration, meaning that we stop processing. We open the circuit. When the alarm goes back to OK again, it will eventually, since we stop sending metrics, it will invoke a step function. That step function would then take a message from the SQS queue and invoke our processing Lambda to see if we are healthy again and can close the circuit. At the same time, we also add a schedule in Event Bridge that every 15 minutes, 20 minutes, whatever you want, invokes this step function to do the same. Picks up the message from the SQS queue and does a test invocation. That way we can easily close and open the circuit on an SQS queue. Everything fails all the time. That's a very famous quote coming from Dr. Werner Vogel's CTO of Amazon.com. And he's absolutely right. In a large enough system, in a large enough distributed system, things always fail. There's always something that is failing. And we need to be able to handle that in our architectures, in our systems, in our components. For example, let's say we take our pizza place. Okay, we are not having an order. The oven is free. We should bake the pizza, but we of course want to schedule a delivery for that pizza, because if we don't want to bake the pizza and then don't have a scheduling appointment to drive the pizza to the customer. So we want to schedule that. But if we get a failure from the scheduling service, we of course want to do retries, right? So we want to retry and handle that failure. But at the same time, we don't want to retry over and over and over again, because if we have a failing service, stressing that service with retries doesn't help it become healthy again. On the other hand, it keeps helping it fail. So what we want to do is we want to retry, but with backoff. That helps us reduce the system strain, and it can help us optimize the user experience. And it can help us save cost by not burning CPU cycles. And what do I mean when I say we're going to retry with backoff? We get a failure from the delivery server. We can't schedule the delivery. So we do retry. Still get a failure. Then we pause for 1 second. If we keep getting a failure, we pause for 2 seconds. 4 seconds, 8 seconds, 16 seconds. Whatever time we want. We have an exponential backoff. We wait more and more and more between the retries. That will help us reduce the strain on the delivery service that this time is failing, and help it become healthy again. But There is a caveat with this, of course. There is a study done, and this picture comes from a blog post by Amazon Web Services, that if you have a huge distributed system, the retries become synced. If the system is large enough and distributed enough, the retries will become synced, as you can see in this picture. We can clearly see that we have the synchronization, because all services wait the same backoff, 1 second, 2 seconds, and so on. So all of our retries become synchronized. What happens if the delivery service become healthy and we have a huge amount of failures? They will be retried at the same time, and I can bet you that the service goes down again. So it's good, but what we want to do is we want to add jitter. So we want to do retry, but we want to add jitter. That way we can avoid synchronized retries, and we can distribute the system load, increase the success rate, and it can be very adaptive. What do I mean when I say jitter? What we do, we retry it after 1 second, 2 seconds, 4 seconds, but on the retry, we add a random number. We add a random weight. That way, not all services will retry after 1 second. Some services retries after 1.2 seconds, and so on. So we evenly spread the load. We add a random weight to the backoff time. So if you look at the same study, but now with jitter added, we can clearly see that the load has been more distributed now. There's no synced retries. There are some in the beginning, but they are slowly fading away. And that is due to adding this random weight to the backoff time. When we implement this, I will return now to the retry envelope. Once again, we use the envelope wrapper. That's why we talked about this in the beginning. And we add a section, retry metadata. That retry metadata can contain information about the number of times we have retried this, what was the timestamp the last time we did a retry, or any additional information we want to add. We're going to base our solutions now on this envelope. So if we're going to implement this, let's say we have our Lambda function that calls our scheduling service to schedule a pizza delivery. Once again, we take that, we wrap it inside of step functions. You will figure out that I love step functions. I use it for everything. Because step functions comes with a very powerful, both retry, but also a catch. So if there is an error, we can catch that error, and we can do our own error handling. So in this case, we get a failure. We use the step functions catch functionality. We do calculation of the wait time. We enter a wait state, and then we retry the Lambda. It's a very clean, very simple way to implement it using step functions. If we have said that we are maximum going to retry this 10 times. Every time we do a retry, we increase or increment the retry counter. So if we, in the calculate time slot, discovers that, oh, wait a minute, we have been trying this 10 times, then we can take the message and move it to dead letter queue, the DL queue instead, for manual handling or different processing later down. It will look something like this. The Lambda function, we try to invoke it. We have a choice state to figure out if we are failing or not. We catch it, and then we do either we send a message to a SQS queue, if we had max number of retries. We do a calculation of the wait time, enter a wait state, and go back to the Lambda function. A different way, of course, if we have an SQS queue, once again, we can't invoke a step function from SQS. So we would instead invoke a Lambda function. Here, what we're going to do, we're going to take a trick. And we're going to use the on-failure destination, which is a feature of Lambda. So when a Lambda function fails, it will invoke the specified on-failure target. In this case, we can have a retry queue. So when we fail, the message ends up in a retry queue. We can have a retry manager. The retry manager picks up the message, looks if there is an envelope. If there's no envelope, it knows that, okay, this is the first failure ever. It can add an envelope and send it back to the retry queue. And now you're thinking, but wait a minute, if you send it back to the retry queue, it will be retried immediately. Correct. So we use a little bit of a trick here. In the SQS, there is a thing that's called visibility timeout. A visibility timeout is when a message is in the queue, but it's considered to be in flight, meaning that it cannot be processed at the moment. What we can do is when we add messages to the queue, we can set the visibility timeout. So the retry manager can say, hey, okay, we have retried this once. We're going to retry again. Here's the random wait time. We're going to wait like 3.5 seconds. We add the message onto the retry queue and set the visibility timeout to 3.5 seconds. That means that the target for the SQS queue cannot pick up that message for those 3.5 seconds. It goes back to the retry manager, it checks the envelope, and invokes a processing Lambda function with a message. What we need to do is both our processing Lambda function, of course, and the retry manager must understand the retry envelope and must be able to handle messages that comes both with and without the retry envelope. There's some resiliency. We can look at some event-driven and messaging patterns in an event-driven architecture. The first one is a Saga orchestration pattern. I think it's as old as computers. I think we all have been using Saga patterns for forever. So I'm going to talk about how we can implement this in an event-driven architecture using choreography. It does support both orchestration and choreography, but I'm going to focus on the choreography part, the event-driven part. It's based on that each transaction in the Saga publishes domain events onto the event bus, telling it what is happening, what it has been doing, created the user, baked the pizza. The benefits of it is that we can introduce very loose coupling between our services. They don't need to understand about each other. Our transaction becomes very self-driving. It introduces a fault isolation. There's no need for other services to fail because we have one failure of the service. If you have one failing service, it will retry till it can process the transaction and move on in the Saga. Creates a very scalable and flexible solution. Consideration, complexity, of course. Always complexity as we add more components, we add more patterns. We need to understand that our system becomes eventually consistent. Because the first service has completed a transaction and said, hey, I'm done. That service then thinks that everyone else in the system has the same state. And that might not be the case, because we could have failures down the line in the Saga. That we need to understand that the system and the data can become eventually consistent, depending on what part of the system you're talking to. We need to have a good way for us to have a good event tracking. Add a request ID, event ID onto your event in the envelope, and make sure you can track the Saga in a good way. And from a testing purpose, how are we going to test this? Are we going to test each transaction, or are we going to test the entire Saga every time? We need to consider how we do that in a good way, depending on what we're doing. And my clicker stopped working. So, once again, AWS implementation. Let's return to the pizza place and let's introduce a pizza Saga. So the first step is, of course, to create an order. We create the pizza order. We have a step function that does that. It fetches information about whoever wants to order the pizza, the address, and so on. And then it adds a message onto the event bus saying, order created. That's the first transaction in the Saga. When we have created an order, we have our oven, responding to that. It will pick up the message order created, add it to SQS queue, and then start baking the pizzas in the pace that the oven can handle the baking. As soon as the pizza has been baked, it posts a domain event, pizza baked, onto the event bus. That's the second transaction in the Saga. When the pizza is baked, that is picked up by the scheduling service. In this case, it picks up this, okay, we have a pizza, we're going to schedule a delivery. It schedules delivery, finds a driver, etc., and then posts the event delivery scheduled. Perfect. That's the third transaction in the saga. And the final transaction is when the delivery driver has delivered the pizza to the customer and posts the event pizza delivered. That's the fourth and the last event, domain event in our saga, and the saga has completed. How long this saga takes depends. It depends on the capacity of the oven, it depends on the processing, it depends on number of orders. A saga can go from very fast to very long time. It doesn't matter. It waits, and we wait for each transaction. We're going to talk about data enricher pattern. And that is something I've been using a lot in event-driven architectures. It's a way for us to enhance or add information to a raw data event. It's easy to integrate with multiple data sources. It's very adapting in if we have changing needs, what data we need to have in different domain events. And we can use a message envelope. So we can have the original message and then add enriched information to the envelope. We need, of course, consider data integrity and security. What if we start adding personal information to the events? Maybe not that good. We need to have data sources that are really reliable, because if you want to enrich the message, we can't have a failing data source, because that will break things. And we need to consider that we add extra latency when we do this processing. So how would we implement this in AWS? Let's say that after a pizza order has been created, we want to add extra information about that order, about the customer maybe. Maybe that the customer is a high member or a returning customer, that we should have 25% discount always, and things like that. So what we do is we post a message, say, enrich event, onto step functions. A step function would then call DynamoDB, Aurora, and so on, and add information about the customer onto the event, onto an envelope, post it back to the event bridge, and the event bridge can then send the message on to the next service that's interested in the saga or in the pattern. I don't know, how many of you saw my talk last year about the connected barbecue? A few of you, nice. This is one pattern I used in that presentation as well. So what I had, I was a bit crazy. I connected my barbecue at home because I needed to know about temperatures and stuff like that. So I had a Raspberry Pi sending information about temperatures in the barbecue to IoT Core, sent it over Kinesis to Event Bridge. Now, that was a raw message just saying, oh, temperature X. I wanted to add extra information to that message so I could enrich it. I wanted to know what was the previous temperature reading. What was the 10 last temperature readings? I wanted to add that onto the message so I could do more advanced logic down the stream. So I did that. I sent that message to my data enricher service that added all the information I wanted to the message in an envelope and then posted it back to EventBridge. Then I could have a couple of different services, A, B, C, and they all filter on different things in the envelope. And we would be invoked for, say, oh, okay, we are breaching a temperature limit or something like that. So very powerful to add extra information onto a raw event. Queue patterns, final part, promise. I won't make you fall asleep. Priority queue. A good way for us to have high-value messages being processed first. So we process messages on the importance of the message and not on the arrival time of the message. It can help us get efficient resource allocation, since high-priority messages get processed first. It has improved responsiveness, meaning that, okay, this is a returning customer, they have this and this status, their orders should always be processed first, put them on the priority queue, be processed then the first time. The considerations, of course, is how do we define a priority? Not everything can be high priority, so what is a high priority message, what's a low priority, what's a medium priority? We need to define the priority of the messages. And there is, of course, a risk about queue starvation. If we don't have the proper definitions for high priority, we can starve the low priority messages or the low priority queue because they never get processed. So if you have a normal, two queues, normal and high, and we have the same processor, we would not, in this case, guarantee that the high priority message be processed at the same time. Could you even see? I don't know if you see. There are different colors of the 1, 2, 3, 4 boxes at least. I don't know if it's visible. But we would not guarantee how they are processed in this case. Instead, we need to do something more a bit advanced. So when the processor picks up the message, it checks the priority. Is it a high priority message? Yes, just process it. If it's not a high priority message, it checks, oh, okay. No, it's not a high priority message. Is the queue empty for priority messages? Yes, it is. Okay, then I process. If it's not an empty high priority message queue, send it back to the normal queue. In this pattern, there is, of course, a very clear possibility for queue starvation in the normal priority queue. If there are always messages in the high priority queue, the normal queue will never be processed. So what we can do, once again, we return to our precious envelope wrapper. And we could add logic into that, saying that, okay, if we have returned a normal message to the queue 3 times, process it anyway. That way we can avoid queue starvation. Queue-based load leveling, very good way to handle spikes. In the very beginning, I told you that the first system I designed used the storage first pattern with API gateway and SQS. What we had at Sony was actually a system where when you started your mobile phone, it sent a message to our system saying that, hey, I'm alive. What we could see is that if you get the new software on your phone, basically 95% of all people install that software at the same time. Don't ask me why. The statistics shows that clearly. You get the new software in the morning, like 95% of the people install it in the evening at the same time. So what we got was huge spikes. Let's say that we rolled out an update to a German market with a lot of phones. We got a huge spike into our system. That had high velocity producers, and our consumers was not that fast. So once again, we had SQS queue after event over API gateway, and both of those scales to infinity like crazy. So we just put the messages onto the queue. And then we can process the messages from the queue in our own pace because real time was not important. We could then protect our downstream services, and we could level the load on our consumers. Consideration, of course, once again, latency. We add latency. Data integrity, because messages are in the queue for a long time, maybe. And how do we handle back pressure? That's the most important one. If the queue keeps growing, because our producers is always faster than our consumers, how do we handle that back pressure? We can add more consumers, of course. And we can add time to live parts to the message, saying that, okay, after 500 seconds, we're going to drop this message. It's not important anymore. So you need to define how you handle your back pressure. A simple way, describing what I just said, API gateway to SQS, and then we have our consumers, in this case illustrated by Fargate. And then we could protect our Lambda or Aurora database and have a smaller instance and level the load. To sum everything up, and I'm 30 seconds left, we looked at base patterns for event-driven messaging. We had a look at the resiliency pattern like storage first, circuit breaker, event-driven patterns like the Saga pattern. We had the priority queue and load leveling with queues. And you also saw some great examples on how you can implement all of these patterns in a serverless way using AWS. With that, I say thank you for listening. Thank you for coming. Follow me on Twitter, and no, I refuse to call it X. Connect with me on LinkedIn or read one of my blogs. Thank you.